Gaussian elimination is what's called an algorithm. It's a prescribed set of steps that will take our system of equations and reduce it to as close to diagonal form as possible. Here are some definitions. One of the common forms is what's called echelon form. Echelon is a word that means staircase. So if you take your system and you perform some row operations, it can get to a form that looks kind of like this. And if you look at it, it looks like a bunch of stairs. In each row, there's going to be the first non-zero number, and they have a fancy name. They're called pivots, or the pivot position. We want to have zeros under our pivot values. So you can see that there are zeros under this pivot. There's a zero under this pivot. Echelon form is not unique. You or I may pick a lot of different operations to get a matrix into echelon form, and the ones that you pick are not necessarily going to be the same as the ones I pick. The thing that we really want is what's called reduced row echelon form, and we're going to abbreviate that RREF. And this is about as close as you can get to a diagonal matrix in your particular situation. It's got the staircase pattern again. It has pivots, but there's something a little bit different. All the pivots have a value of 1, and there are zeros above and below all of our pivots. So if you take a look at any one of these columns that has a pivot, there's always a zero above and below that pivot. Now, unlike before, reduced row echelon form is unique. RREF is unique. And this is a theorem. A theorem is an important mathematical result. And what it says is no matter what steps you take to get your matrix into this form, and no matter what steps I take to get my matrix into this form, we will both end up with the same final result. So Gaussian elimination is a way to get our matrix into reduced echelon form. So you're going to put your system into RREF. So I want to walk you through how to do it. I'm going to take this particular system. The variables in this particular system are x, y, and z. It's got 3 equations, 3 unknowns. Put this into augmented matrix form. That's the system that I'm going to work with. We want to create reduced row echelon form. We are trying to create a 1 in the leftmost pivot position. So I'm going to take this matrix and I'm going to try to do row operations to make it have a 1 in that top corner. It's going to be really helpful for you here to swap row 1 and 2 because everything in row 2 is divisible by 2. So here is my first operation. I'm trying to get a non-zero number up in this top corner. Once I've got that up there, I'm going to scale. I'm going to take a half of 1 and make it the new 1. Divide everything in that top equation by 2. This is really good. Having that row in the top makes my life a lot easier. So now that I've got a pivot up there, the next thing that I want to do is create zeros under the pivot with row replacement. So I take a look at that top equation and I say, okay, I'm going to try to do some multiples of this 1 to eliminate the 3 there. I can only add equations here. That's what row replacement's about. Take -3 bunches of equation 1 and add it to equation 2 to make the new equation 2. The top row stays the same, and I use it to create zeros underneath. So -3 times 1 plus 3 is 0. -3 times 0 is 0 plus 6 is still going to give me a 6. -3 times -3 is a 9, plus a -2 is going to give me a 7. And -3 times -4 is 12. 12 plus -4 gives me an 8. I'm not messing with the third equation because it's already got a 0 in the pivot position. Now I have created a pivot with a value of 1 and it's got zeros underneath it. So what I do now is I repeat. This is why it's an algorithm. An algorithm takes a set of steps and then repeats it over and over and over again. I've got the next pivot position. I need to create a 1 there. I'm going to swap rows 2 and 3 because I've already got a 1 there. So 1, 0, -3, -4, 0, 1, 2, 3, 0, 6, 7, and 8. Now I have to create a 0 under this pivot. So that's pretty straightforward to do. I'm going to take -6 bunches of equation 2, add it to 3 to make the new 3. So the top row is unaffected. The second row is unaffected. So 0 and 0, when you add them together, you're not going to have any difference in this first entry. -6 bunches of 1 added to 6 is going to give me a 0. -6 times 2 is -12 plus 7 gives me -5. And -6 times 3 is -18 plus 8 gives me -10. And you can see already that we are in an echelon form. We've got the staircase, we've got pivots because they are non-zero numbers. I'm going to take this last row, I'm going to scale it to turn it into a 1. So I'll have 0, 0, 1. If I divide both sides by -5, I'll get a 2 here. Now I am in triangular form. This is echelon form. Now you might be following along with me, and I encourage you to follow along with me. Your echelon form might look different than mine. No matter what steps you do, the final reduced echelon form is the same. And that means the pivots have to be the same no matter what you do and what I do. You would still have to have pivots in these same spots. The last thing that we need to do is create zeros above the last pivot. And that means I'm going to use replacement. And it's a little bit different. Now, the last equation is the building block that I'm going to use. So I'm going to take -2 bunches of equation 3 and add it to equation 2 to make the new equation 2. So I'm leaving the top alone, and I'm trying to create a 0 using this pivot to eliminate that value. Because there are zeros in that bottom row, adding them to the first entries is not going to change anything. But -2 bunches of 2 added to 2 gives me a 0. -2 times 2 is -4. Added to this gives me a -1. I have now created 1 0. I got to create another 0. So 3 bunches of equation 3 added to equation 1 gives me the new equation 1. So this will turn into 1, 0, 0. 2 times 3 gives me 6. 6 added to -4 gives me a 2. Everything else is the same, and I am now in reduced echelon form. It's diagonal. It's so easy to read the answer off. Z is 2, Y is -1, and X is 2. I can see there's only one solution. So the solution set is 2, -1, and 2. Now you might think, oh, I can do it better. Why did you do this? Or can't I do it some other way? Do I have to write it in the matrix form? Yes. This is the best and most efficient way for you to solve a linear system. And this is the one calculation we will do all semester. So it's really important to take the time to understand it now because we're going to use it for the rest of the semester. So our goal is going to be to try to do this to every system. Now, unfortunately, not every system has a diagonal RREF. And we're going to talk about what else could happen.